Okay, in this lecture we're going to cover our section 3.4 material on motion in space. And in this section we're going to be applying some of the concepts that we've been considering in our earlier chapter 3 material related to vector functions or space curves to study the motion of an object through space. So we've already mentioned that we could think about a space curve as representing the trajectory of some object moving through 3 dimensions. And using some of the calculus of vector functions, we can answer questions about the object's velocity, speed, acceleration, its total distance traveled, sort of how rapidly it's changing its tangential direction along the curve, using these concepts that we've considered in our previous sections. So in the beginning of this section, we're going to talk about velocity, acceleration, and speed of an object. So let's introduce these concepts with the following definition. So here, let's suppose that r of t is a twice differentiable vector function, which can be used to represent the position of an object as a function of time. So if this is a 3-dimensional vector function, its graph is some space curve, and we're going to view this curve as an object's trajectory through space over time. So given that assumption, we would say that the velocity vector of our object is given by the vector function v of t, which would be the derivative of our position function. So the rate of change of position would be our velocity. And the speed of our object at a time t would be given by the magnitude of the velocity vector. So if we don't care about direction, if we just care about speed, whereas velocity is speed plus direction, we would simply take the magnitude of the velocity vector, and that is what we call speed. And the acceleration vector of an object at time t would be given by the vector function a of t, which would be the derivative of our velocity vector v prime of t, or the second derivative, r double prime, of our position function. So given these new definitions, let's look at some examples. In our first problem, we are told that the position vector of an object moving in space is given by the vector function r of t, where t is non-negative, and we are asked to find its velocity, speed, and acceleration at time 1. So let's start by finding our velocity. So the velocity vector, v of t, is the derivative of our position vector, r of t. So for our first component, we would have a 3t squared. For our second component, we would have 2t. And for the third component, 3t squared. Now we wanted the velocity at a particular moment in time, namely when t is equal to 1. But let's maybe find just an expression for the speed at any general time, or the acceleration at any general time first, and then we'll evaluate these at the specific time of interest. Now, once we have the velocity vector, we can find speed as the magnitude of this velocity vector, and that would be the square root of the sum of the squares of the components of this velocity vector. So squaring the first component, we would have 9t to the 4th, plus the square of the second component would be 4t squared, and the square of our third component would be 9t to the 4th. Or simplifying a little bit, we would have the square root of 18t to the 4th plus 4t squared or if I factor out a t squared from the expressions under the radical, I would have an 18t squared plus 4. And taking the square root of this expression leaves us with t times the square root of 18t squared plus 4. Now our acceleration vector, a of t, would be found by differentiating the velocity vector, v of t, or equivalently, by finding the second derivative of the position function. So in any case, our acceleration vector would be 6t to 6t. Now, we were asked about the velocity, speed, and acceleration of this object at a particular time, namely when t is equal to 1. So let me say at the time t equals to 1, we would have a velocity v of 1 of 3, 2, 3. So this is our velocity vector of the object in space. The speed would be the magnitude of this velocity vector. So either using the expression that we found earlier, or taking the magnitude of this vector, which we just found, we would have the square root of 9 plus 4 plus 9, which would be root 22. Note that that's the same thing we would get if we substituted 1 into the general expression that we found for speed earlier. And our acceleration at time t equals 1 would be given by the vector 6, 2, 6. Okay. So let's look at another example. Here we are asked for the velocity, acceleration, and speed of a particle that has the position vector r of t given here. So again, let's start by finding our velocity vector, v of t, which is defined as the derivative of the position vector. So here we would have e to the t, 2, and negative e to the negative t. For the acceleration vector, a of t, we would be differentiating the velocity vector, or equivalently, taking the second derivative of the position function, which would give us e to the t, 0, e to the negative t. And then to find the speed of this particle, we would be looking at the magnitude of our velocity vector, which would be the square root of e to the t squared, which is e to the 2t, plus 2 squared, or 4, plus negative e to the negative t squared would give us a positive e to the negative 2t. So this would be our velocity, acceleration, and speed for the particle that follows the trajectory defined by that position function. So if we have a function or a vector function which represents the trajectory of an object through space or even through the plane, it's not difficult to find its velocity, acceleration, or speed. We're just looking at the first couple of derivatives of position, or for speed, the magnitude of that velocity vector. So let's look at some examples where maybe we're moving in the opposite direction. So suppose that we have information about the velocity or acceleration of an object, and we're trying to find its position function. So as an example, we're told that a moving particle starts at an initial position given by r of 0, which is 0, 1, 0, with an initial velocity of v of 0 equals 1, 0, 1. and its acceleration vector is given as a of t, whose components are shown. So we are asked to find its velocity and its position at any time. So if we have the acceleration vector, which is the derivative of our velocity vector, we could work backwards to find the velocity vector by finding the antiderivative of this acceleration vector. So that is, I'm going to define the velocity vector v of t as the antiderivative of this acceleration vector. So finding the antiderivative component-wise, we would have a 1/2 t squared, 1/3 t cubed, and 1/2 sine of 2t. And we could add some arbitrary constant vector, c1, and notice that I'm putting a vector arrow above this arbitrary constant. So I'm not just adding a scalar on the end of this, I'm adding a vector of scalars. And before I can find the position of this object, well, I need to solve for this constant vector c1 using the information that I'm given about the initial velocity of this object, which was the vector v of 0 equals 1, 0, 1. So making use of that initial condition, if I look at v at time 0, well, if I plug in 0 for t in the vector that I just found, I would have 0, 0, 0 plus c1. So really I would just have the vector c1. And I'm told that this has to equal the vector 1, 0, 1. So our velocity vector v of t is given by the sum of this vector function plus the vector c1, which we just found to be 1, 0, 1. So summing those two vectors component-wise, my first component for the velocity vector would be 1/2 t squared plus 1. My second component would be 1/3 t cubed plus 0, so just 1/3 t cubed. And then 1/2 sine of 2t plus 1. So this would be the velocity vector for this object. That was one part of our problem, finding this velocity vector. Now we were also asked for the position vector of this object at any time t. And if we know the velocity vector, which is the derivative of our position vector, then we could calculate the position vector r of t by finding the antiderivative of the velocity vector v of t. So finding the antiderivative term by term or component-wise, for the first component, we would have 1/6 t cubed plus t. For our second component, we would have 1/12 t to the fourth. And for our third component, we would have negative 1/4 cosine of 2t plus t. And again, I could add some arbitrary constant vector, I'll call it c2, to that vector function to get my most general antiderivative. Now I need to find the specific constant vector c2 that satisfies the initial condition about our position function, r of t. And I was told in the problem that that initial position was r of 0 equals 0, 1, 0. So let's see what we have here. r at time 0 would be equal to the vector 0, 0, negative 1/4 plus this constant vector c2. And I'm told that that had to equal the vector 0, 1, 0. So solving for this constant vector c2, I would have 0, 1, 1/4. And once I know c2, then I have my position function r of t. It's defined as the sum of this vector function with c2, where c2 was this vector 0, 1, 1/4. So taking the sum of those two vectors, we would have a first component of 1/6 t cubed plus t, a second component of 1 over 12 t to the 4th plus 1, and a third component of negative 1/4 cosine 2t plus t plus 1 over 4. So this would be our position function for that object. So by making use of an antiderivative of a vector function, we can find the velocity or position of an object given its acceleration and some initial condition about its position or its initial position or initial velocity. Now in the last part of this section, we're going to introduce something called the tangential or normal components of acceleration. So I'll mention that in some applications, if we're studying the motion of an object, it would be useful to consider breaking our acceleration vector down into two components, where one would be acting in the direction of the unit tangent vector, and the other would be acting in the direction of the unit normal vector. And those components of our acceleration vector are what are called the tangential and normal components of acceleration. So to illustrate this, let's suppose that we have this space curve, C, or maybe just a curve in the plane as it's shown here. And for any point on this curve, so for any point in time, we have some acceleration vector describing the acceleration of our object. So say this vector A here. Now, in some applications, we might be interested in determining how much of this acceleration vector is acting in the direction which lies tangent to our curve. So that is the direction defined by our unit tangent vector, and how much of this acceleration vector is acting in a direction which is normal to our curve, which would be defined by this unit normal vector n. So the tangential and normal components of acceleration are these components of the acceleration vector acting in the direction tangent to the curve, or the direction normal to the curve. And these are denoted as A sub t or A sub n for the tangential and normal components of acceleration. So let's see if we can introduce or derive a formula for the tangential or the normal component of acceleration. So let's consider the tangential component of acceleration. So what I'm really looking at here is the following. Let's suppose that I have the line, which is determined by the unit tangent vector. I'm trying to find the scalar projection of the acceleration vector onto that unit tangent vector. So recall the vector or scalar projection of one vector onto another. What we're interested in is the scalar projection of the acceleration vector onto the unit tangent vector. So this tangential component of acceleration, which I'll denote as a sub t, is really the scalar projection or the component of the acceleration vector projected onto the unit tangent vector t. Now in our chapter 2 material, we had derived a formula for this scalar projection of one vector onto another. So here this would be defined as the dot product of a and t, that is my acceleration vector and the unit tangent vector, divided by the magnitude of the unit tangent vector. So let me maybe write these as functions of t to distinguish. So acceleration, my unit tangent vector, and its magnitude are all functions of t here. So let me write that just to be clear. Now, we know that by definition, capital T of t, that is the unit tangent vector, is a unit vector. So this magnitude of the unit tangent vector is 1, since it's a unit vector by definition. So we really just have the dot product of our acceleration vector with the unit tangent vector. So let's think about this. The acceleration vector for some object was defined as the second derivative of the position vector, that is r double prime of t. And we're taking the dot product of that with the unit tangent vector, which by definition is r prime of t divided by the magnitude of r prime of t. So taking this dot product, we would have for our numerator the dot product of r double prime of t and r prime of t. And we're taking that scalar and dividing by the magnitude of the tangent vector r prime of t. So this is a formula for the tangential component of acceleration in terms of the derivatives of our position function, r of t. Now, in a similar way, we could define the normal component of acceleration as the scalar projection of the acceleration vector onto the unit normal vector, which by definition is the dot product of the acceleration vector with the unit normal vector divided by the magnitude of the unit normal vector. And again, since by definition that unit normal vector is a unit vector, its magnitude is 1, so we're left with the dot product of our acceleration vector and the unit normal vector. Now, making use of some other expressions which we've seen involving curvature in our last section, we can simplify this formula for our normal component of acceleration a bit more to involve only the position vector r of t, and we arrive at the following theorem, which gives us formulas for the tangential and normal components of acceleration. So formally here we would say if r of t is a vector function which is used to denote the position of an object as a function of time, then a of t, which is the second derivative of position, would be the acceleration vector. And we would define the tangential and normal components of acceleration, which are denoted by a sub t and a sub n, as follows. So the tangential component of acceleration is the dot product of our acceleration vector with the unit tangent vector, which we said is given by the dot product of the first and second derivatives of position over the magnitude of our derivative of that position function. So it's the exact same formula that we obtained up here. And the normal component of acceleration, which is denoted a sub n, is simply the dot product of the acceleration vector with the unit normal vector, which can be shown to be equal to the following. The magnitude of the cross product of r prime and r double prime divided by the magnitude of r prime. So given these formulas for the tangential and normal components of acceleration, let's look at an example. So here we are asked, or we're told, a particle moves with position function r of t given here, and we are asked to find the tangential and normal components of acceleration at a general point and at the origin. So to make use of the formulas that we just derived for tangential or normal components of acceleration, we need to first calculate a few things. So let's start by finding the first two derivatives of this vector function. So here r prime of t would be 3t squared, 2t, and 1. And the second derivative, r double prime of t, would be 6t, 2, and 0. Now once we have these, we want to calculate the dot product of these two vectors, which would be given by 18t cubed plus 4t plus 0. And we also want the cross product of these two expressions. That is r prime of t cross r double prime of t, which would be given by the determinant of a 3x3 matrix whose first row consists of the standard basis vectors I, j, k. Our second row would be the entries of r prime, which were 3t squared, 2t, and 1. And our third row would be the entries of r double prime, which are 6t, 2, and 0. So for this cross product, our I component would be 0 minus 2, so negative 2. The j component would be 6t minus 0, or just 6t. And the k component would be 6t squared minus 12t squared, or negative 6t squared. So the last bit that we still need to calculate would be the magnitude of the derivative of our vector function. So looking back at our first line of work where we found r prime of t, taking the magnitude of that vector, we would have the square root of 9t to the fourth plus 4t squared plus 1. And we need the magnitude of the cross product of r prime and r double prime. So taking the magnitude of our cross product, which we found above, we would have the square root of 4 plus 36t squared plus 36t to the fourth. And once we have these components, we're ready to find our tangential and normal components of acceleration. So again, the tangential component of acceleration was given by the dot product of r prime and r double prime, which we found to be 18t cubed plus 4t, over the magnitude of r prime, which was the square root of 9t to the fourth plus 4t squared plus 1. And the normal component of the acceleration vector, a sub n, was given by the magnitude of the cross product, which we just found to be the square root of 4 plus 36t squared plus 36t to the fourth, all over the magnitude of r prime, which is the square root of 9t to the fourth plus 4t squared plus 1. So these would be the tangential and normal components of acceleration at a general point. And then we were also asked for these values at the origin. So let's consider what value of t represents the origin. So at the origin, which is the point 0, 0, 0, we find that t would have to be 0 by setting our vector function equal to the point 0, 0, 0, and we find, of course, that t has to be 0 here. So substituting 0 into our expressions for the tangential and normal components of acceleration, we find that the tangential component would be 0 over the square root of 1, which is 0. And the normal component of the acceleration vector would be root 4, or 2, over root 1. So we would have 2.